In this video, we're going to write a program for the TI-NSpire CAS app, which will do a numerical integration of the area under a curve. And we're going to be using the left rule Riemann sum to do that numerical integration. And you can see an image here of the way that that integration proceeds. One draws little rectangles that fit underneath the curve and that intersect the curve at the left upper point of the rectangle. And then you simply sum the areas of those rectangles. As the number of rectangles increases, the closeness of the fit to the curve and the exactitude of the area under the curve increases as well. Now we're in the TI-NSpire CAS iPad app, and we're going to begin this project by creating a new document. And we're going to start by adding a graph to that document because we want to take a look at the function that we're going to be integrating using the left rule. And that function is going to be f of x equals 2 minus x squared. So let's take a look at what that function will look like. And we're going to integrate it from the 2 points at which it intersects the x-axis. Now, it's pretty easy to see that those 2 points are minus the square root of 2 and the square root of 2. But let's just show that clearly here on the graph. And one way of doing that is to add a second function here that is simply y equals 0. So f2 of x is going to equal 0, and we'll add that function in as well. And now we can look for the 2 intersection points. And we do that by going up to the wrench tool and do analyze graph and do intersection. And we're going to pull this line over to one side of the left-hand intersection, and it expands out to the other side, and we're going to just hit that there. And we'll see that negative 1.414, which is negative square root of 2, an approximation of negative square root of 2, is the left-hand intersection point. And we'll do that again, analyze graph, intersection, we'll pull it over to the right-hand one, and we'll see that this time it's positive 1.414. So it's that area between the 2 intersection points in the positive y portion of the graph. That's going to be the area that we're going to be integrating. Now, it's pretty obvious to us where the 2 intersection points are of the function f of x equals 2 minus x squared with the x-axis. But let's just look at another way of determining those points. We're going to add a calculator to this document, and we'll do it this way. And we're going to do solve, and we're going to solve 2 minus x squared equals 0 for x. And we see that this gives us those same 2 intersection points. Now we're going to begin working on our program, and we're going to use the TI basic programming language, which, although there's some variation from calculator to calculator about what's allowed, for instance, with variable names and how lists are dealt with, it runs pretty commonly across the set of TI programmable scientific calculators. In order to access that function, we're going to add a program editor to our calculator app, so to the calculator portion of this document. So we'll come down to functions and programs and add program editor and new. And we're actually going to start by adding a function. We're going to call that function simply f. And for this program, we're going to change that to be a function. And we're going to say OK. And we're going to define the function. We're going to need to send, this is simply going to be the function of f of x equals 2 minus x squared. we need to send the function the parameter that we want to be used here. And we're going to call that parameter b within the confines of the function. So we're going to call it b. And we're going to create a local variable here. And we're going to call that g. Then we're going to say that, we'll go back to get the calculator keyboard here. And we're going to say that 2 minus b squared, and we're going to store that, and we can store it using the variable. Sorry, we can store it using the holding down on variable and using store. 2 minus b squared we're going to store in g, and then we're going to return g. Now we need to save this function, and so we'll go up here to check syntax and store. Check syntax here and store, and now we see f stored successfully. So over on this left-hand screen, we now have a workspace in which we can test some of this. So let's try seeing what f of 1 will be. Simply 1, because 2 minus 1 squared equals 1. Let's try f of 2. And that's minus 2, which is what we would expect. Now that we have the function defined, let's go up and start working on our program. To that, we're going to add another program editor to our document, to the calculator space in this document. So we'll use the wrench tool, and we'll come down to functions and programs, and program editor, and new. And this time we're going to write a program, and we're going to call that program left rule. Left underscore rule. And it's going to be a program, and we are going to give this one library access. We will give it library public, show it in the catalog. Okay. Now, this program is going to need to have we're going to need to tell the program how many segments we want to be dividing the area to be integrated into. How many rectangles are we drawing? And we're going to call that number n. And n is going to be the number of points here. And we need to define the beginning point and the end point of the integration. So we're going to say that negative square root of 2 is going to be stored as our starting point for the integration. So again, we come up, hold variable, and go store. Oops, sorry, that went under the square root sign. Hold variable and do store. And we're going to store that as the variable p1. And positive square root of 2. So positive square root of 2 is going to be stored as the variable p2. Now, we need to define the width of each of the rectangles, and so that is going to be just p2 minus p1, all divided by the number of rectangles that we're doing, and that's going to be n. And so that is going to be stored in the variable d. And finally, we need a variable that will be holding on to the area as we go through each point to sum up the area, and we're going to call that a. And obviously we have to initialize that, start it with 0. So we're going to do 0 gets stored in the variable a. Now we're going to create a loop that will actually do the summation of the areas of each of the rectangles that will give the estimate of the area under the curve. So we're going to create a for next loop here. And so we'll come up here to the wrench tool, and this is going to be a control function in the program. So control, and then we can just come down to for, end for. It's going to put in the beginning point and the end point of that loop for us. See, it says here for and end for. And we're going to call our looping variable I, and we're going to go I from 0 to n minus 1. We're going to choose an I for each of the left-hand points of each of our rectangles. And we have n minus 1 because we're starting with 0. If we were starting with 1, we'd go up to n, but we're going to start with 0. And now, what's the area of that rectangle? Well, we're going to need to choose the function at the left hand, at the height of the left hand point on the rectangle. And so we're going to say that we need to get the x value of that left hand point. So P1 plus I times d is going to get stored in x. Is going to get stored in the value in the variable x. And you can see that P1 is the starting point of the integration, and then the I plus d is the distance of that next rectangle, of the x value of its left-hand edge. And so P1 plus I times d is going to get stored in x. So now we need to be adding to the sum of our total area under the curve, which we're calling A. And we're going to take the old value of A and we're going to add to it the value of f. So we're going to call this f of x, remembering that x is the height of the left-hand edge of the current rectangle. And that's going to be times d. And that's all going to be stored in A anew. And that, if this loop runs correctly, that should sum up for us the total area under the curve, an approximation. Now we want to display that. Now that we've finished the loop, we want to display that. So DISP, and we're going to display the approximation of A because we don't want it to try to prettify it somehow or another into a nice math statement. Instead, we want the numerical answer, so approximation of A. Now that we've finished our code, we need to store this program. So we'll come up to the wrench tool and choose check syntax and store, and we'll check the syntax and store it. And we see that it's been stored successfully. Now we can come back over to the left-hand side, our calculator side here, and let's take a look. If you tap on var, down here you'll see a list of the possible variables that we can choose from, including the functions and the programs. And so we'll choose left rule, or you could have just typed in left rule. And let's try this with 5 rectangles and see what we get. 3.62039. Now let's try it with 10 rectangles and see what we get. 3.733. Now let's actually do the integration and see what the answer is by doing out the integration. So we're going to come up to the rectangle tool. We're going to choose calculus. We're going to choose integral, and we are integrating from minus square root of 2 up to positive square root of 2. The function 2 minus x squared dx. And we're going to ask for an approximation of that. So we'll come down here and do a numerical approximation. 3.77124. So our 3.733 with 10 rectangles did a pretty good job. Let's see what we do if we get 50 rectangles, how close we'll get with that. So we'll come down here and choose left rule, and let's try it with 50 rectangles. 3.76, and let's just try it with 100 rectangles. 3.77. So we see we're getting down now to the third or fourth decimal place in terms of how close we get to the right answer, and that's doing pretty well. So we'll try in future videos. We'll try other methods of Riemann sums and compare them to what we saw with the left rule integration. Thank you. It's good having you here, and we hope to see you again soon.